Hello everyone and welcome back. As promised, in this session we are going to learn about the binary multiplication. So, without any further ado, let's get to learning. Coming to the outcome of today's session, today we will at first observe the basic binary multiplication. Thereafter we will observe something called the partial sum approach in binary multiplication. Let's begin with the basic binary multiplication now. Say we are multiplying two different bit patterns, and in that we are selecting the multiplicand, which is denoted by m, as 1010, which is 10 in decimal. On the other hand, the multiplier denoted by q, we are selecting that as 0110, which is 6 in decimal. So let's perform the multiplication now. Now this is the LSB of the multiplier, right? And it is 0. So if we multiply 0 with all these 4 bits, we will get the answer as all zeros. Now coming to the next bit of the multiplier, this is 1. Now observe carefully, this is not the LSB, right? This bit is actually placed in the place value of 2 raised to the power 1. So this is not the LSB. So once we perform the multiplication of this bit with all these bits, whatever the result that we might obtain, we can't store them in this place. Rather, we will start storing them from this place onwards. And what is the reason behind that? The reason is, the multiplier bit is from the bit place which holds the place value 2 raised to the power 1. Now this is 1. Multiplying these 4 bits with 1, we will obtain the result as 1010. Now what about the next bit? This one has the place value of 2 squared. Therefore, we won't be able to use these places. And since it is 1, the result that we are going to obtain will be 1010 only. Now coming to the MSB of the multiplier, it is 0. Now multiplying these 4 bits with 0, what we will obtain? We will obtain all zeros. Now if we perform the addition, the least 2 places will be zeros. Now from here we will obtain 1. Here also we will obtain 1. What about these? Here we are going to obtain the result as 1 only. And the same can be stated for this one as well. And this one is going to be as it is. So basically we multiply 10 with 6. Therefore we are supposed to get the result as 60. So let's check whether we have obtained that or not. Observe the places. This one has the place value 1. This is 2. This is 4. This one has the place value 8. This one has the place value 16. Thereafter, this one has the place value of 32. And this one has the place value 64. So 32 plus 16 will give us 48. And 48 plus 8 will result in 56. Thereafter, 56 plus 4 will generate the result 60. So yes, multiplying 10 with 6, we are obtaining the value 60 only. Now this is the basic binary multiplication. Let's now observe the partial sum approach. Now before we dive straight into the partial sum approach, let me illustrate something very interesting. Say our m, that is the multiplicand, is of n bits, and also suppose the multiplier, that is q, is also of n bits. Now with this organization, the multiplication of m and q at worst case may generate a result which will be of n plus n, that is 2n bits. Let me illustrate this. Say we are performing a multiplication where the multiplicand is 1111, that is 15 in decimal, and the multiplier is also the same. Now if we perform the multiplication, we will obtain this value, and observe how many bits did we obtain? 1, 2, 3, 4, 5, 6, 7 and 8. So yes, multiplying 4 bits, at worst case, we may get the result of 8 bits. Now just for the sake of completion, observe, we performed multiplication between 15 and 15, right? So 15 squared is actually 225. Let's see, did we obtain that or not? Now since we have 8 bits in here, the place value of the 8th bit is 128. And the respective place values are 64, 32, 16, 8, 4, 2 and 1. Now observe the placements of the ones. 128 plus 64, that will give us 192. 192 plus 32 will result in 224. And 224 plus 1 will result in 225. So yes, performing the multiplication of 4 bits, that is 2 15s, we are getting the answer as 225. Now honestly, I haven't shown you the addition process in here, but I will request all of you to perform the addition on your own and observe how beautiful this addition is. Anyway, coming back to our illustration. So what did we learn? If the multiplicand and the multiplier both are of n bits, at worst case, the result of m into q will be of 2n bits. This is an important piece of information, and this is going to be used in the partial sum approach. Basically, in order to store the result, we are going to use a 2n bit register. Let's now observe the partial sum approach. So, for every bit in Q, that is the multiplier, and we have to traverse the multiplier from right to left, that is in the reverse order. If the bit is 0, basically while traversing the Q, that is the multiplier from right to left, if we come across the bit 0, we are supposed to perform a right shift once on the register's content. Now what is this register? This is the 2n register, which will initially be cleared with zeros, and the content of that register we are referring to as register's content. Similarly, if the bit is 1, first we are supposed to add the entire multiplicand with the most significant n bits of the register's content and then perform right shift once. Notice this one very carefully. If the bit that we have come across is 1, we are supposed to first add the entire multiplicand with the most significant n bits. This is a bit interesting. The addition is performed with the contents of the register and with m, but we are supposed to add the register's contents most significant n bits with the m, that is the multiplicand. Say the multiplicand we are choosing is 1010 like the previous one only. Similarly, we are choosing the multiplier, that is q, as 0110. Now coming to the register, it will be of 8 bits because both the multiplicand and the multiplier are of 4 bits each. So 4 plus 4, that is 8. And initially, these are supposed to be cleared with zeros. Now in the partial sum approach, we are supposed to mainly focus on q, that is the multiplier. And we are supposed to traverse that from right to left, that is from the least significant bit towards the most significant bit. Let's now start the process. Observe, while we traverse this from the LSB towards the MSB, the first bit is 0, right? And what we are supposed to do when we come across the bit 0, we just have to perform right shift once on the register's content. So this is the register's content. So we will perform the right shift now. Performing the right shift will clear up this space, and here we are supposed to place 0. Now this is the first right shift that we have performed already. Now coming to the next bit, that is 1. Now what are we supposed to do when we come across the bit 1? If the bit is 1, we have to first add the multiplicand with the most significant n bits of the register's content, right? So this is the multiplicand that we have. Now this is of 4 bits. So we will add these 4 bits with the 4 bits of the multiplicand, that is most significant 4 bits, right? Now these are all zeros and this is 1010. So we will get the result as 1010. Now what about the remaining bits? They will remain same. Now we are not done yet with the second process. We are still in here because after we perform the addition, thereafter we are supposed to perform the right shift once again. So let's perform that. Now we are done with the second process. Now the next bit in the multiplier is 1. So we are supposed to add the entire multiplicand with the most significant 4 bits of the register content. So let's perform that. Now interestingly enough, the content is 0101 and here the multiplicand is 1010. So performing the addition, we will obtain the result as 4 ones and the remaining bits will remain the same. Now we are again supposed to perform the right shift. So let's do that. Now we are done with the third bit. Coming to the fourth bit, it is 0. And when we come across the bit 0, we are supposed to perform the right shift only once. So let's perform that again. Now we are done with all the bits of the multiplier and this is supposed to be our result. Now observe, during the basic multiplication, this is the result that we obtained, which is almost same as this one. The only difference is we have one more bit in here as the MSB. And since it is 0, these two actually hold the same value, don't they? So using the partial sum approach, we are still getting the same result. Now let's observe some technicalities. Basically in this partial sum approach, we have done mostly 2 things. First, the right shift. Secondly, the addition of the multiplicands. So how many times did we perform the right shift? Observe. This is the result of the first right shift. This one is the result of the second. And these two are the result of third and fourth right shift respectively. Now if you observe our process so far, we are performing right shift in both the cases, right? So the number of right shifts will be n. Now what is n? That is the size of both multiplicand and the multiplier. Now how many times did we perform the additions? Here it is 2. And why these additions happened? These two additions happened because of these two bits. Whenever we came across 1, we are supposed to perform addition. So the number of additions can be determined by the number of ones in Q, that is the multiplier. Now these two rules are pretty important for this partial sum approach. And this is how the binary multiplication using the partial sum approach is carried out. So in this session, we observe the basic binary multiplication first. Thereafter, we observe the partial sum approach in binary multiplication. Alright people, I hope you understood the concept of basic and the partial sum approach of binary multiplication. In the next session, we will observe the idea behind Booth's algorithm for binary multiplication. So I hope to see you in the next one. Thank you all for watching.